Hello, and welcome to your Chemistry 1412 mini lecture over half-life and mechanisms. While there are different definitions for each of the different reaction order half-lives, today we will focus on just the one, first-order half-lives. Radioactivity follows first-order decay. We will discuss nuclear reactions at length further along in this course. Half-life is the time that it takes for something to decrease its value by 1/2. First-order reactions have constant half-lives. If one solves the integrated first-order rate law and solves for T and uses the ratio of 1/2 for the ratio of A subscript T to A subscript naught, the result is the equation for half-life in terms of the rate constant K. The 2 in the natural log function comes from that ratio of 1 to 2 mentioned earlier. Some textbooks show the natural log of 2 as 0.693. If one enters 2 and then takes the natural log in their calculator, you can get the full irrational number. It is better to use this as the value rather than 0.693. To fully understand how reactions take place, one needs to consider the reaction mechanism. The reaction mechanism can be thought of as the step-by-step description of the reaction mechanics. Each of the steps are called elementary reactions. When one adds the elementary reactions together, the overall reaction is observed. Reaction mechanisms are useful for many reasons. They can elucidate how catalysts speed up a reaction. They can show intermediate species which were hidden by the overall reaction. They can also give insight on how to optimize the reaction rate. Here are all of the different types of elementary steps. If the sum of the coefficients of the reactants is 1, this reaction is called a unimolecular reaction. If the sum of the coefficients is 2, it is a secondary reaction. If the sum of the coefficients is 3, it is tertiary. Tertiary elementary reactions are exceedingly rare. Quaternary elementary steps are not observed. Each elementary step can be used to write an elementary step rate law. Unlike rate laws of overall reactions, which have exponents which must be obtained through experimental data, elementary step rate laws have exponents that are equal to the corresponding coefficient of the reactant. One can use all of the elementary step rate laws and a little algebra to mathematically determine the mechanism. We will see more of that later. In our last example, we had a slow step. It was step 2. The slowest step governs the rate of all of the other steps, and so it's called the rate determining step. It is possible to derive the overall rate law with a little algebra and the elementary step rate laws. Look at step 1 above. Here we have 3 proposed elementary step rate laws in the form of 3 equations with 3 unknown concentrations. By solving for one of the unknowns and then doing a substitution, we can get rid of the intermediate and have left over a rate law which is only in terms of the reactants in the overall reaction. The key is to remember that the fast step is reversible and therefore has 2 equations, or elementary step rate laws, which can be written. Set them equal to each other, and then solve for the intermediate. Substitute the obtained value of the intermediate into the slow elementary step rate law, and voila! you have the overall rate law. The rate constants k are combined into one value to become the overall k, which is determined by experimentation. A mechanism is the step-by-step breakdown of all the reactions that happen behind the scenes of the overall reaction. Mechanisms are broken down into elementary reactions. Each elementary reaction is a step in the mechanism. These elementary reactions have a type according to the sum of the coefficients of the reactants in that elementary reaction. If the sum equals 1, it is a unimolecular elementary reaction. If the sum equals 2, it is a bimolecular elementary reaction. If the sum equals 3, it is a termolecular elementary reaction. Sum equals 4 does not exist. Even sum equals 3 is extremely rare. The speed of a reaction can be hastened by warming up the reaction vessel. Warmer temperatures mean more velocity to the molecules in the liquid, which means they collide more often, which means that the chance of an elementary step occurring goes up. Chilling the reaction vessel will slow down the reactions. If you do many experiments of the same reaction but at different temperatures, you can plot the results as shown here and extract some useful information. A, which is called the pre-exponential factor, is related to the molecularity of the elementary steps as well as the spatial difficulty involved in each elementary reaction. Capital E subscript A is the activation energy, which is the energy needed for the reaction to move forward to form products. As you can see here, the activation energy is like a hill that the reactants must climb in energy in order to proceed to the products. If the energy of the reactants is less than the energy of the products, that reaction gains energy to get to the higher value, and it removes that energy from the surroundings, leaving them feeling colder. This is an endothermic reaction. If the energy of the products is lower than the energy of the reactants, energy is being lost to the surroundings, which feel warmer, and the reaction is exothermic. A catalyst will speed up the reaction by lowering the activation energy. More particles in the reaction will have sufficient energy to overcome the lower activation energy, which means more products can be formed in the same time frame, hence the increased rate of reaction. This has been your mini lecture for 1412 covering half-life and mechanisms. Please go to Sapling and do the associated assignments at this time. If you run into trouble, don't hesitate to ask for help. I'll see you next time. Bye.